In this video, I'm going to be talking about trusses. Specifically, I'm going to be talking about the 2021 HSC Engineering Studies paper and K-Trusses. Now, I have said several times that I think that students should typically only bother learning the method of sections. The method of joints can be useful at times, but generally I say that only me and Snoop Dogg bother to use the method of joints. Well, Snoop Dogg has been everywhere this year. He was on Menulog ads and he was serving people KFC from the drive-thru. And he seems to have been influential on this paper because they've specifically asked for the method of joints. And the way that they've sort of tried to push you in that direction is that they have given us a question that has two fixed reactions. Now, my reading of the syllabus, and I'm not going to show the specific wording because you can look at that yourself, is that calculations should only involve reactions that show either two cases. One case is a pin and a roller, and the other case is a fixed cantilever. They're the only two cases that we should be doing calculations for. I can see the argument here is that the HSC doesn't want you just to take the reaction and have a simple method of joints question. They want you to do some more work for your 3 marks. And I haven't had an opportunity to talk to other senior engineering studies teachers to talk to them about whether or not they would pay working out that, because I know that as of 2021 you have to show working out to get marks. If I was marking this as a trial paper, I would never write this in my own trial, but if I was using this in a trial, I would personally still give marks for students who use the method of sections. That's how I would approach it. So I would cut through this line here, and then I would, cut through this line here. I would have two distractors I would have here and here, so I'd take moments about B, and that would give me my forces. And measuring from B, I would just take the distance. Anyway, it wouldn't even necessarily go to the effort of calculating the distance from B to the perpendicular distance here. I can do that using trigonometry. I could find this angle, and then finding that angle, I could then I'd make BC the hypotenuse. But I don't even necessarily think I would do that. If I was in a hurry, I would just I would scale this 4 meters, and I would just calculate a value of D. I'm not here to talk about that. What I'm here to say is that it is possible, and I would say 50-50, that you will only get 2 out of the 3 marks. Now, the first thing I would say is it takes a lot of effort to use method of joints a lot of the time, and you are better off getting 2 out of the 3 marks than 0 out of the 3 marks. So even if you're going to lose 1 mark for using the wrong method, you're better off using the wrong method than not attempting the question at all. That would be my first point. The second point is that they've asked us. There's now a question where they've asked us specifically to solve using the method of joints. I still think it's relatively difficult. It's not immediately apparent how to solve it with method of joints, but effectively we can just do the trigonometry of this triangle here to find ED, and then we do the next joint, which is C. And so we will then we'll know CE. Knowing CE gives us enough information that we can then calculate the joint at C. But I want to put it out there, because I've said in the past that method of joints is not usually required. That is no longer true. There is now a precedent to say that you could be asked for method of joints. The next thing I'm going to talk about is K-Trusses. I had a student who asked how he would solve this K-Truss and whether or not method of joints is a good way about it. Method of joints is always a good way to solve an entire truss, but I'm going to show how this could be solved using method of sections. So the first thing I'm going to do is I'm going to create this truss on my student has already done that for me, that they've done their truss. The problem is I don't want to use their irregular units. I want to use consistent units, and they've applied they found a load of 73 newtons. They got 7.3 kilograms. They multiplied by gravity. That's the values they had for the truss that they had designed. I just want to make life a little bit simpler, so I'm going to draw up my own one in the Johns Hopkins Truss simulator. Now, I've already put the nodes in place, but I'll just point out that the nodes go together a lot better than they used to. In the past, you kind of had to just click and hope that it was close enough. Whereas now you can really actually, not only does it snap to locations, to grid locations, but you can actually specify exact positions. So this can be useful when you want to do something like an equilateral triangle, so that you can set it as the height of the position as 86 or maybe 87, or like 0.87 units north. Now, so what I've done, I've already got my nodes. I'm now just going to add in the members, because I don't think I have any videos showing how to draw this. I think drawing the nodes is pretty simple, so I'm not going to go back and do that again. But I'm just connecting all the members, and I'll just point out. So I've already shown that you can adjust the locations of nodes. And I'm pretty sure we can do that on the fly. Now, the big thing that I found is that if you make a mistake, you kind of have to delete the node to be able to make a mistake. So what I'll do is I'll just quickly move node 8, and I'm going to set this to 1. We'll see what happens. Okay, so we can see it moved that location. Now, if I accidentally connect a member, so from here to here, and I don't want that member to exist, so then I can go to delete single. Now, I think you have to delete the whole node. So I'm just going to draw that node again. Now, it looks like it's in the right spot. 15, node 15 is in the right spot. Okay, and connecting the members. Now, I have to apply a pin and a horizontal roller, otherwise it won't work. I'm then going to add a force. I'm going to add the force to the top because that's what the student has done. And I'm going to do that. I'm going to add 1 unit of, actually, I'm not even too concerned. I'm just going to pick a number. So I've got that 130. So what I want to do is I'm going to adjust that to say I want that to be 100. So I'm going to set that value to 100. So this is how I can set up an actual case from the textbook or something like that, and I can get my answers. Then I'm going to solve once, and you can see that's pretty busy, right? I can't really see what's going on very easily. So what I'm going to do is I am going to change the scale. So I'm going to zoom in. Yeah, zoom in, and I'm going to pan. Hopefully that was the right way. That was the wrong way. There we go. That looks pretty good. And I can make it show arrows, but in this case, they show compression in red and tension in blue. I hate that convention, but that's what they're doing. We can't see the value of this member in the middle. We know it's compression because we can see the red box, but that's because there's a 100 Newton force directly over the top of it. So that's how it's going to go. So we're going to try and solve that. I'll just quickly talk about K-trusses that do exist. So this is a K-truss in America. The Long Island Bridge. There's a K-truss in Germany somewhere, and in Australia, if you go to the Central Coast, there is a K-truss, a 2-span K-truss, the Pete's Ferry Bridge, which is on the way to Mooney Mooney. So that's that another angle of it where you can see just that side, the 2 spans on this side. So what I'm going to do now is I'm now going to record on the camera, and I'm going to splice these 2 videos together. Continuing on with what it said on the computer, we're now going to go through this, we're going to solve this truss here. So the first thing we want to do is we're going to solve these members. So I'll point out that another student had done a K-truss like that because he said, well, that way we'll get rid of the zero force member, but that's not true. So having an extra line here, all that does is just add additional weight. It might help with, say, bracing, if we've already talked about zero force members in other videos, that they can be used to prevent buckling, and they can be used for different load cases. But just because that's, once we make this a zero force member, well then this one, it's as this, so this line doesn't exist. And so what we have now is we have 3 forces meeting at a supplementary angle, so this is going to be a zero force member. And so we can have a chain reaction of zero force members. So those 2 are zero force members, we can just ignore that straight away. So we're now looking at the next easy location. So I'm only going to solve half of this truss because I'm not really interested. It's symmetrical, so if I only solve half this truss, I'm going to be happy. So I can. Am I going to remove it? Yeah, I'll give myself some more board space. I've set these each at 1 unit, and 1 unit and 2 units tall. I've set it to 45 degrees, so that makes things fairly easy. Okay. So, the first section that I'm going to look at is this AB and AC. They're pretty self-explanatory. Like that's typical joints, and this is typical trusses. And that's a good opportunity for me. This is where I would use method of joints. These corners are a very simple opportunity to use method of joints. So what I would say is looking at I get my magnifying glass, I'm going to zoom in at joint A. If we zoom in at joint A, what do we get? Well, at joint A we're going to have an external force of 50, and we have AB, the internal force at AB and the internal force at AC. We know that these three forces need to be in equilibrium. If these three forces are in equilibrium, that means they're going to fit on a vector diagram. So I'm going to draw those forces up like this. So I say, well, that's 50 going up, and I know I have AC, and I know I have AB. They're going to mean something like that. And if this is going up, well, relative to the center of this shape, is going clockwise or anti-clockwise? Yeah, it's going anti-clockwise, so these also have to be going the same way. And I say, well, if this is 50, what percentage of this is a triangle? So just knowing that we have... Okay, so I get a little bit 60-degree happy because 60 degrees is so common in our designs. So rather than using these values, which is what we typically use for most trusses, because most trusses we get are going to be at those angles. In this case, the ratio we have is we know that we've specified that this is 2 high and 1 across. So in that case, this hypotenuse is going to be √5, and that means our angle is going to be 60. I've done the trigonometry off camera. It's going to be 63.4, just to save the pain of you watching me hit buttons on a calculator. So now that we have that triangle, what we're going to do is we're going to calculate what this value could be. Now there's a couple of ways I could do that. What I could do is I could take the ratio, or I could take the trigonometry. I personally like ratios a little bit more than I like trigonometry, so I would rather take 25, like half of 50 times √5, but you know, different people are going to have different ways of approaching that, and that gives me an answer. I'll just check with 55.9 is what I got, and that's what the calculator gets. That's what the truss analysis says. Okay, so 59.90, and this is going to be 25. This is going to be half of 25 because there's a ratio of 2 to 1. That's how I would go about doing this, and then when we label our diagram, I'm not going to label the diagram yet because I'm going to keep these ones up for a second because I actually want to solve BD before I start using any known values. Just to demonstrate that's how we approach it. So I will quickly do this through method of sections because this is how I want most people to remember how to do trusses, even though personally I really like method of joints for the edge cases like this. I just felt the compulsion to draw that. Okay, so what we would do there is we would just take our section, would be very short. We would say that we have a force of 50 going up, which means we're going to have 50 going down. In order to have 50 going down, we're going to have a diagonal on AC, and if AC has a vertical component of 50, that means its downward component is going to be 59.9. So if ACV equals 50, then its diagonal is going to have to equal 59.9. Now, if we take, to find out AC, what we would do is we would assume tension, AC, and we'd say sum of the moments about, we take moments from B, equals 0, 0 equals, and we're going to have AC multiplied by 0 because it passes through that location. We're going to have 50. 50 is going clockwise, and it is 1 unit away. And we're going to have AC, which is 2 units away. Now AC, we have assumed tension, and it is in tension. If it is in tension, it's going to be anti-clockwise. So what we can do is we can say that AC times 2 equals 50, so therefore AC equals 50 divided by 2, AC equals 25. And because it's positive, it means that we're just going to say everything is in newtons, and that means because it's positive, our assumption is correct, which is tension, which is what we see here. We're going to draw all that up in a second. What I want to do first is I want to show how we solve BD before I start adding these things to the board. So what I'm going to do is say, well, if we have our cutting plane that happens, I want to choose this cutting plane. The reason I want that is because it's got 3 members that we're going to cut through. That's going to be where we're going to cut. So I'm going to draw my little model of that, and it looks like this. These are the members that we're cutting. So we're going to have an external force of 50. Somehow erased that earlier, so I'm going to put that in. And we're going to assume tension on all of these. We've got AC. Oh, I didn't label this point. I need to give that a name. EFG. I think I get to L. P. And Q. Yeah, I like that. Okay. So we've got BQ. And BD. Now again, why am I drawing arrows out? Because we have an assumption that we assume tension when we use method of sections. So what I want to do first is I want to find BD. So to find BD, what I'm going to do is I am going to say, to find BD, I want to find a location where these two meet up, which they meet up at C. So I'll take the sum of the moments clockwise measured from C equals 0. 0 equals, and we're going to find BQ times 0, AC times 0. We're going to have 50. 50 is going clockwise relative to C. So 50 times, and it's 1 unit away. We're going to have BD, which is 2 units away, and so it's clockwise. And BD is also clockwise. So plus BD, assuming tension, which is 2 units away. So already I can see that it's not going to be in tension, it's going to be compression. So what I'm going to say is minus 2 BD equals 50. So therefore BD equals 25 newtons . 25 newtons, and it's going to be in compression. Just checking, yep, and that's what we've got there. Okay, so what I'm going to do is I'm going to start labeling these in now on the diagram. So in this case, if I want to label this on the diagram, the convention is we say, well, BD is compression, so that means it's going to be pushing into the node, so we'll go like that. And we said AB is, we calculated AB. We can just see, by observation, we can see if we have 50 going up, there's only one diagonal that can provide that vertical force. AB is going to have to be pushing down into this node. So that means it's going to be in compression. So we've got AB equals 59.9. We had AC, we said AC was in tension, and that's 25. Now I wanted to try and show that we don't need to use any of these existing values to find BD. That's how we get our start. To find BQ, it's actually not BQ, it's actually BP. Sorry. I'm going to put that in red just so we can correct people. Okay, I'm now going to clear this side of the board to keep going. What we're going to do now is find BP. Okay, to find BP, well, to find BP, so what we're going to say here is BP, in this same cut, we have BP and we have two other members. We have BD and AC. If BP is our target, our distractives are BD and AC. So what do those things, they don't meet, so it means we have to use the meetup method, we have to use the lone wolf method, otherwise this thing is unsolvable. Right? So if they don't meet this, we have to use the meetup method. So what we have is BP, so we know that BP is going to have to be the same value as our vertical force. Our vertical force is 50, we don't have any other, our unresolved vertical force is 50, so we're going to have 50 going down. There's only one member that can do it, that's BP, so 59 is going to be going down. So down is pulling out of the node, so out of the node is tension, so we draw that like this, and we say 50. Okay, we've already found PC from observation, so next thing we're going to do now is, this is where we start to get a little bit more difficult, is we're going to try and find these members. Now, at this point, we do need to use previous knowledge, right? So it becomes a little bit more like using a method of joints question. So what I'm going to do is I'm going to show, we're going to cut, our line is going to cut like this now. Our line is going to cut like this. So let's see how that goes. That's our cut. Okay, so I'm going to label some things. We're going to label this as 25, because we already know that. I'm not going to label it by its name, because we've already solved that value. For BD, we've already solved that as well, so I'm going to show that as it's going into the node. 25. Then we have PD. We have PE, and then we have PC, which we've solved by observation, as we know that it should be a zero force member. So what we have now is we have two unknowns. So to solve this, what we need to do is we need to take moments about a location. So we can see, if we're trying to find PD, our distractor is PE. So PE needs to be resolved. What we do is we now say, well, where is a location where we can take moments about PE that doesn't also pass through PD, because otherwise everything will multiply by 0 and that won't be good. So what we're going to do is we're going to go to point E. Yep. So there's a PE only really passes through two locations, through P and E, so we want to go through point E, that way we can find it. Now, while I'm here, I'll say, well, what's our perpendicular distance? Our perpendicular distance is going to be, in this case, it's going to be, if this is a triangle, if we have 1, 1, root 2, which means that for a 45-degree triangle, if this is 100, this is 70.7%. Okay, so this will be, if this is 1, this will be our root 2, which is 1.412, something like that. Okay. So to find PD, what I'm going to say is sum of the moments clockwise, sigma moments measured from point E equals 0 and 0. So what I'm going to say, first of all, I'm going to say PE multiplied by 0. And then I'm not even going to worry about PC. I'll just say PC times 0. Yeah, I just write PC because it's a zero force member. I'm going to have PE, which is what our target is. So, sorry, PD, which is what our target is. And we just figured out what PD's distance is. We said it was root 2, which I'm pretty sure is 1.41. Maybe 1.42, I think. 1.41. Good, okay. Now, is it going clockwise or anti-clockwise? Relative, we're assuming tension. We're assuming tension. So relative to E, that's going clockwise. We then have our minus 25 brackets. It's 2 meters away, or 2 units away. It's going anti-clockwise, so it stays as minus. And we have this, we have 25 times 0, this one here, which AC, it passes through E, so it doesn't count. So before I forget this 50 up, which this is a problem I have with sometimes when I draw my diagrams, I forget to add, include all the external forces. So this is 2 units away, 50 times 2, and it is also going clockwise. So what we're going to get now is we're going to say, we're going to have 100 minus 50. So we're going to say 100, we're going to have 1.41 PD minus 50 plus 100, which is we're going to get 1.41 PD equals minus 50 PD. So if we have, so police departments when I see PD, if I had 1.5 PDs and that owed me $50, well, we're going to get a smaller number if we have only 1 PD. So 1 gives me something like 35.36, and because negative means our assumption was not correct, so it's Newton's compression. So compression like that. Okay, for PE we're going to do exactly the same concept, except this time we're going to just take moments from a different location. So we know, I'm going to correct this and say, well, we know that PD is going in, so we're just going to write it as PD. And we've got our 25 going in here, but we're going to find PE. We know we have this force. Now I'm not being consistent. Okay, so what we're going to do now is this time around we're going to take our moments from D. Now our perpendicular distance is going to be the same. Our perpendicular distance is going to be the same, so now we're going to take some of the moments about D equals 0, 0 equals, and we'll just go through all of our forces. So we also have this force here, that's 0. Okay, so we have 25 multiplied by 0, we have PD multiplied by 0, we have PE. Now PE is going anti-clockwise around D. Yep, PE is going anti-clockwise around D, and it's 1.41, so it's going to stay as negative. We're going to have our 0 plus 0, this is our 0 force member. We're going to have our 25, so it's going anti-clockwise around D, so we're going to have minus 25 times 2, and then we're going to have 50, which is going clockwise. 50 times, now how far away is it? It's 2 units away. Okay. Yeah. Okay, so what are we going to get? Well, first of all, we're going to move this over to the other side. So we're going to say 1.41 PE equals, and then these are going to be cumulative, so we're going to say it's 50 and 25, it's 2 units, that's 2 units away. This is clockwise. That's better. Okay, so what we're going to have is minus 50 plus 100 equals 50. So we get the same number, just the difference is this time around we won't have the negative. So we're going to have 50 divided by 1.41 equals 35.3. Our assumption was positive, the assumption was correct, so we're going to go, our assumption is correct. So, assumption is correct, so it's going to be in tension. So, we're going to draw that now in here. That's tension, so it's pulling out from each node. 35.3. Okay, now, this is we're now at another location where we're going to talk about using method of joints, right? So mixing this in, that we could, quite reasonably, especially now that we have all these knowns, we could find CE by taking moments about, say, B, right? Taking moments about B. If we take moments about B, so now to find CE, there's two ways we can go about it, and I'm not probably going to do all as much working out at this point. We're going to cut just vertically, like that. And we're not going to forget to add our external forces, because that's where I get in trouble. And because we already know these forces, did it the wrong way. We can, we could, if we wanted, we could do a sum of the vertical, sum of the horizontal forces. So we know the horizontal forces here and here are going to cancel out. So if we have the horizontal forces here and here are going to cancel out, it means that we only have one horizontal force left, right? Which is, this is going to have to be in tension, 25 newtons. That's one way of doing it. Another way is that we could take some of the moments about a location like D, and we take some of the moments about a location like D, we will still get that same answer. We'll have this known force, and we can calculate our answers with that one force. But in this particular case, it works with some of the forces because we know that this happens to cancel out. The alternative is we can use the method of joints. And so what I'm going to do now is... So the alternative is we could use method of sections here. Method of joints here. So I'm going to clear this off and... So what we could do is we could zoom in on location C. And when we zoom in, I don't really want to zoom in that much. What we're going to get is these forces. So if we're told that, or we've already calculated that this is 25 this way, and we know that this is a zero force member from observation, well, this has to be also in 25 in tension. Right, so that gives us that answer. So we have multiple ways of finding CE, and we're going to get that CE is in tension. So what we're going to look at now is how we do the rest of this truss. And the point here is I'm not going to do calculations for these. I'm just going to talk about the method that I would use to solve it. That way I'm going to make fewer mistakes and have to do less edits. Okay, so we're now going to find DF. And when we look at we've got DF is our target, DQ is our distractor, and we have some other values, but they all meet at the same location, E. So for DF, what we're going to take is, in this case we'll say sum of the moments measured from E, and that'll help us to find DF. Looking at this, we can see, well, if this is 50 and it's 2 away, right, this is 50 and it's 2 away, it's going clockwise, Well, if all of these here cancel each other out, then this is going to have to be going back the other way, which is going to be, means compression. And so we're going to set dF equals 50 in compression. All right. For dq, to find dq, well, we can say, even without knowing df, we should be able to find dq as well. Dq is actually not too difficult. So for dq, if we look at this, we do have, okay. So I was going to say, initially I was going to say we can find dq just on the basis of the sum of the vertical forces. That's true, but we'd have to figure out the vertical component of this. So that's one method that we could use. Am I happy to go that way? Yeah, we could do that way. Yeah. The alternative is, if we already know df, we can take some of the moments about here would be good. Some of the moments about, so for dq, where we're going to take some of the moments about. Yeah, let's just use vertical method. That way we don't need to worry about df. So what we're going to say is, what is the vertical component of this? Well, if we say that this is 35.3, that means its vertical component is going to be 25 10. Right? So in that case, if we're taking the sum of the forces vertically, in this cut, what we're going to have is we're going to have 50 going up. We're going to have 25 going down. That's going to be this vertical component of PE. So we'll write that as PEV. PEV equals 25. And then we're going to have the remainder, which is going to be dq. And so dq is also going to have to equal 25. So it's 25, it needs to be going down in order to maintain equilibrium. So if it's going down, that means it's pulling out of the node. If it's pulling out of the node, it is in tension. So 25 in tension is what our calculations say. So that gives us those two members. Then to find these members, we're going to do a similar concept, right? So to find E and yeah, I'll just draw it up. We're going to find E and G. Okay, so when I'm drawing these, especially if you're drawing in pencil, it's actually easier just to draw the whole thing and then to draw your cut again. So what we want to try and find is we want to try and find here E and Q. So what we're trying to find is we've got EG, EQ. We're trying to find those members. So what we can do is just cut through the smallest number of members that goes through those. Like that. Okay. We already knew this one here is 25 going in. We already know this one here is 35 going in. And we then have our unknown, which we'll label like that, as EQ. And we have EG. And can't forget the external force. Okay, so in this case, if we wanted to find EQ, we use exactly the same method. We can find that using our sum of our forces vertically. So I've used green. I used green to show that I didn't really want to use the full working out. So yeah, I'm going to stick with that. So sum of the forces vertically. I don't normally write it that way, but hey, you know what? I see all sorts of odd things. So what I'm going to have is I have 50 going up, and I have this value here is the same. So what are we calling that? PD. PD. So we're going to have PDV. PDV equals 25 down. So that means we're going to need to have an additional 25 down at EQ. So that means this will not be going that way. Our assumption is incorrect. It's going to be going into the node. So it's going to be in compression. Now, another way we could have approached that is we could have taken moments about a method of method of joints at this location. So let me just, so we're going to say it's going into the node. It is going into the node. Let me just check. I've said that several times, so if I'm wrong, yep, that's right. Okay, 25 into the node. Now, how else we could have approached that is we could have said, we don't know yet that, sorry, I was going to say we could have taken method of joints, but at this point we don't know that these two are going to be the same. I have to prove that, and we don't know that yet. Okay, so we've found EQ. We've done that. The next thing we're going to do is we're going to find EG. So what we can do is if we take moments about D, everything lines up with D. These meet up with D, EQ lines up with D, so it's actually pretty easy. So we can say clockwise, sum of the moments measured from point D equals 0. What are we going to get? Well, this cancels out, so what we're going to have is, we have, this is 2 units away, 50 times 2, 0 equals 50 times 2 clockwise, and so that means this is going to have to be anti-clockwise to balance it, and how far away? It's also 2 units. So we're going to say plus EG times 2, that's assuming tension. We're going to get out, it's going to prove that that isn't the case, so we're going to say EG, those 2's cancel out, EG equals 50, negative, therefore, compression. Okay, so, and so yeah, we get 50 in compression, blue is compression on that. Blue is tension. Blue is tension. That's clockwise. This needs to be anti-clockwise. Whoops. Anti-clockwise. Anti-clockwise, that's going to be negative in our assumption. Tension. I am kind of rushing this a little bit. I'm not doing the full working out I would normally do because I don't really want to solve this many members. Okay, so it's in tension. Okay, so what we're left with now is this location. So what we can see is we're now going to zoom in on location Q. If we zoom in on location Q, without knowing exactly what's going on, what we can see at location Q, what do we got here? We're going to have this K shape, and we've got 25 going so that's in compression. Compression's into the node, tension is out of the node. Okay, so 25. So there are forces, and then we have FQ and GQ. So we know that we're going to get a triangle that looks something like, if we draw that as a vector triangle, we're going to have 25 plus 25 is 50, right? And then we're going to have, at our 45-degree angles, this is going clockwise around that dot. Sorry, going anti-clockwise around that dot, so they're all going anti-clockwise around that dot. if I have a triangle, 1, 1, root 2, you can see that over there. So that means that this ratio is going to be 100, 70.7, 70.7. So in that case, this is going to be half of 70.7, which is 35.36. 35.36. 35.36. Okay. That's how I would solve that. That's how I would solve point Q. I would switch up and I go to method of joints there. But we can also look at the vertical forces. So what we need to know though is we need to know that these two are going to be equal at this point. We can prove that they're equal because I'll show you how we do that. Right? I'm going to clear the board and I'll prove to you how we know that. Eraser's not great, so forgive me. Okay, method of joints. So what I'm going to do is, like I said before, I'm going to draw the whole thing because otherwise it's really easy to make a mistake. Right, you draw the wrong shape. It's just really, and then once you've got that, you can then say, okay, well, I'm now going to make my cut. My cut's going to be really simple. It's going to be like that. And I'm going to remember to add in my external forces because that's what gets me into trouble. And you'll notice I'm saying that over and over again because I want to remind you and me of this. So what I can say now is if I cut here, I do know this force here is 50, and this one here is, it's also going to be 50, right? Yep, 50. Okay, so these forces cancel out. So if we take the sum of the moments, sorry, sum of the forces horizontally, if we say sum of the forces horizontally equals 0, we know that 50 and 50 cancel out. So what we're going to be left with is FQ and GQ. So what that means is we can then say FQH equals GQH. And because they're at the same angle, because they're at 45 degrees, that means we can say we know that they're the same. We know that they're the same value. Now, what we can then say is, well, we have a leftover value. We have a leftover value of 50. So we know that FQV plus GQ, GQV equals 50. Right? If we've got 50 going up, well, what's going to need to balance it? We're going to need to have these. They can't cancel each other out. They're going to have to be both going the same way. They're going to have to be GQ and FQ, and they're going to have to be equal to 25 and 25 because they can't cancel each other. Then we know they're equal, and they have to add up to 50. So that means that we know the vertical component of these is 25, and we know if the vertical component of these is 25, so if we say GQV equals FQV equals 25, and it has to be going down, if it's going down, that's going to give us this number of 35.36 down. So that's going to be going down. GQ stays the same. GQ stays the same, and we now can correct this one to say we know this one has to be in compression. And that gives us that answer. Okay, so that's going into the node, that's going out of the node. 35.6, 35.36. Now, that leaves us with one last part of this that we need to solve, and that is this member FG. Now, FG, there are two ways we can go about it. What we can do is we can take we can take a big long cut. So I'm going to show you how we can do FG. I'm going to clear the board. to solve the top of the, to solve this last section, FG, what I've done is I've drawn a diagram. Now it's not perfect, but that doesn't matter because we're going to take our section line like this. Now I realise that I've had an error. I wrote this down as 59 instead of 55. So with that correct, what I'm going to show is if we label all our forces, right? It doesn't actually even matter, but we'll just draw the arrows so we get the idea. We have this going in and out. We have this one going in, out, in, out, in, out, like that. Now, if we look at location B, and this will be true when you do it for location B, we'll draw without even doing the maths behind it, we could say that we could break this into the vertical component of AB. We could take the vertical component of AB, but what we're going to say is, well, AB only has three components, and BD doesn't do vertical. So that means that if we take BD out of the equation, because it can't take a vertical component, the vertical component of AB and PB, they have to cancel each other out. If they don't, we won't have equilibrium. So they have to have equilibrium at that location, so those forces cancel out. And the same for their mirror. When we go to the next location, when we go to D, it's starting to get a bit messy now. I'm going to leave the same. What have we got here? Here we have 4 members, but BD and DF, neither of them have horizontal components. So that means that PD and DG, the vertical components of those have to cancel out. So those can also be removed. They're no longer in our equation. Now, several times now I've said that it's important that we remember to include our external forces. So let me not forget that 100. So we're going to have FG, and then we're going to have the vertical component. So the vertical component of FG, FGV, and this is going to be, what's that called? FQ. Vertical component of FQ. And the vertical component of FQ, we've done several times, is 25. And the vertical component of its mirror is also going to be 25. So then we can do fairly simply, because we've eliminated so many of these, because we know they cancel out, we can say the sum of the forces vertically equals 0. And what we can say is 0 equals minus 100 plus 25 minus FG plus 25. So looking at this equation, we can see that in actual fact, if we have 100 going down, we have 50 going up, so the missing amount needs to be going the other way. So that means FG is actually not going down, it needs to be going up. So it means my initial assumption was wrong, our assumption of tension is wrong, so we're going to change it to there. And so now what we're going to get is, I'll draw it as a diagram. So if I have 100 going down, 100 down, and I have 25 up and 25 up, the missing amount is going to have to be, which is FG. FG is going to equal 50 up, which if it's going into the node, that makes it tension. Sorry, if it's going into the node, has to be going into the node is compression. So, into the node is compression. So, what does that look like if we just do our last magnifying glass here at F? What do I have? Well, I have DF in its mirror. I have the external force of 100 down. I have FQ in its mirror, and then I have FG. FQ, FG. Now, if we take FD FD, and we say, well, FD is going 50 that way, we know that its mirror is going to bring it right back. So we can kind of ignore it. And then we have the 100 down, which is our external force. The external force of 100 down. And then what we're going to do is we can add to that FQ's mirror, which is 35. And we know that at the other end we have FQ. So they're both 35.36, 35.36, and then what we have in the middle is 50. Right? That gives us the same idea. It's going into the node, so it's in compression. Okay, that gives us how to solve the thing. The point here is, yeah, for your assignment, really don't do the K-Truss unless you're a glutton for punishment. It's hard to show that much working out. Yeah, hopefully that was of some value.